I'm going to do a brief video on electron dot structures and Lewis structures. Sometimes they're called structural formulas. For those of you who, excuse me, weren't in class, haven't been in class the last couple days, I'm hoping this will be useful for you when you try and get the homework done, particularly the homework about Lewis structures. So some things to keep in mind as we learn how to draw electron dot structures or Lewis structures. Some things to keep in mind. First, the octet rule. Atoms like to have 8 valence electrons, right? We've been talking about that since first semester. So if you look at fluorine, for example, in this molecule, this F2 molecule, fluorine starts out with 7 when it's alone, but it forms a molecule with another fluorine so that it can have 8 valence electrons. So each fluorine starts out with 7, and then between them they share a pair so that they can have 8. That's why and how nonmetal atoms bond to each other, by sharing electrons. Now this is called the dot structure, and you can see why. Each of the electrons is represented as a dot. This is sometimes these expressions are used interchangeably, dot structures and Lewis structures. And I do that without thinking. If I'm really, when I look at something like this, that's what I call a structural formula, okay? And sometimes I'll use Lewis structures interchangeably. I don't want you to get too hung up on the vocabulary behind it. I just want you to be able to be comfortable drawing one or the other types of structures, either the dot structure or the structural formula. Okay, so again, the octet rule is what drives bonding between nonmetals. There are exceptions to the octet rule, though, and you already know 2 of them. Hydrogen and helium, they don't have they will not accommodate 8 electrons. They can accommodate 2 and no more than that. Another exception that we have not spoken about is boron. Okay, boron is atomic number 5. Sorry, it's atomic number 5, and it can hold 6 electrons. So it is also an exception to the octet rule, where it fills with 6. I'm not going to go through the notes too much. What I really want this to be is practice drawing Lewis structures. And for those of you who did miss class today, I'll try and fill in as we go. I've got 15 minutes before the video cuts out, so I want to kind of just get a move on. So when we are drawing dot structures or structural formulas or Lewis structures, whatever you want to call them, what we are doing is we are drawing the connections between the atoms in a compound. So here I've got silicon and I've got fluorine. The name of this would be silicon tetrafluoride. Okay. Now you'll notice that I have 5 atoms altogether. 1 silicon and 4 fluorine. I have to decide how they connect to each other, right? And I do that again by keeping in mind the octet rule, the rule of 8. Okay, too lazy to write out octet right now. I'm also, when I'm learning how to do this, I may be a little confusing as to what is the central atom? Is there a central atom? If we look at the periodic table, maybe these notes will be better. If we go back to our notes right here, and I talked about this in class today, there is also a pattern. So we're going for 8, but there's also a pattern on the periodic table that we haven't really talked about yet, and we haven't had a reason to until now. And remember, we're talking about molecular compounds, which means nonmetals only. Okay. If we have carbon or silicon, the two nonmetals that are in this column, they like to form 4 bonds. So carbon likes to have 4 bonds attached to it. Okay. Nitrogen, as you move to the right of the periodic table, nitrogen and phosphorus, but I'll stick with the top row, nitrogen and phosphorus like to have 3 bonds with 2 lone pairs. Oxygen, if you can see the pattern shaping up, likes to have 2 bonds and 2 lone pairs. Okay, and then finally the halogens, we'll use fluorine. Fluorine likes to have, the halogens like to have like to have 1 bond and 3 lone pairs. Okay, so generally speaking, carbon doesn't like to have lone pairs. Nitrogen likes to have 1. Oxygen likes 2. The halogens like 3. That's not a hard and fast rule, but it's fairly typical. Okay, we're going to stick with some simple structures to start with. So keep this pattern in mind when you're looking at the periodic table. The other thing to keep in mind is the closer the element is to the center of the periodic table, okay, the element that is closest to the center of the periodic table is going to be the central atom. And if you think about this, the ability to form bonds and lone pairs and all of that, right, it would make sense that carbon would be a central atom because it can form the most bonds. It also makes sense that fluorine can't be a central atom because it only forms 1 bond. It's only going to be on the periphery, right? It can't really be in the middle of anything because it can only form 1 bond. It can't be between anything. And then hydrogen, which is up here on the periodic table, that also just forms 1 bond, but it doesn't like lone pairs. And the reason I mention hydrogen now with the fluorine is that, like fluorine or any of the halogens, hydrogen will be kind of on the periphery as well. It's a terminus. It doesn't go anywhere. It can't bond. It can't connect to things. It's just kind of floating around on the edges, so to speak. Okay, so the further in you get on the periodic table, the closer you get to the center. That's the element that will be your central atom. And sometimes there's more than 1 central atom, but we're just going to kind of start simple. So if I look, I've got silicon and fluorine here. Oops. Silicon is here, right under carbon. Fluorine is right there. So I know that silicon's going to be in the middle. I also know that silicon likes to form 4 bonds. Okay, so that's something to keep in mind. Before I get started, though, what I want to do is I want to make sure I know how many valence electrons I have to work with, because it's valence electrons that make up bonds. It's not core electrons. And I only have so many valence electrons. I have a specific number, and I've got to make them work. It's kind of like a puzzle. So silicon tetrafluoride, we'll start by counting up how many valence electrons there are altogether in these 5 atoms. First of all, silicon is right under carbon on the periodic table. Anything in that column has 4 valence electrons. Okay, so that 1 silicon will bring 4 to the party. And then I've got 4 fluorines. Fluorine is a halogen. Halogens have 7. Remember, they're closest to the noble gas configuration. They just need 1 more. So 4 times 7, 14, 28. So my total number of valence electrons that I get to play around with here is 4 plus 28. That's 32 valence electrons, which sounds like kind of a lot. You'll see that it actually can go pretty quickly. Okay. So I know silicon's going to go in the center. I know silicon needs to have an octet of electrons. That's what's driving all of this. So I'm going to put 8 electrons on silicon since it's in the middle, and I know it likes to make 4 bonds. And then the only thing that it can attach it attach itself to, the only thing we have are fluorines, right? So they're going to be, I'm going to draw this over here at the same time. Okay, I'm going to do both the structural formula and the dot structure. So you can decide which one you prefer. Some people really like the dots because you can count up all the electrons. Some people like the dashes because it's easier to kind of see what's happening. Okay. One thing to keep in mind, if we're doing this type of structural formula, each line represents 2 valence electrons. It represents a bond, and in each bond there are 2 valence electrons. All right, I'm going to erase this. All right, oops. So I have placed 8 valence electrons. There are 8 around silicon in both of these models. So 32 minus 8, that gets us to 24. Now, I've got 24 more to place. Right now, silicon is filled. It's got its valence electrons. It's got the 8 it wants. But if you look at each fluorine only has 2. So each of them needs some more. I'll start with this one. This fluorine has 2, it wants 8. So I'm going to give it 6 more. 2, 4, 6. Okay, and I'm going to do that for each fluorine. 2, 4, 6. 2, 4, 6. 2, 4, 6. So I had 4 fluorines, and I gave each of them 6 more electrons. 6 times 4 is 24. So I have just placed all of those 32 electrons, right, on this one. And then I'm just going to do that over here as well. So each fluorine gets 6 electrons. Now, these models are depicting the same thing just in a little bit different fashion. Okay. And notice this also follows the pattern that I was talking about on the periodic table, where silicon and carbon like to form 4 bonds, and halogens like to have 1 bond with 3 lone pairs around them. Okay, so that's how I would draw the structural formula or the dot diagram or the Lewis structure for silicon tetrafluoride. All right. I'm going to stop this video, and I will do another one with I will have a second video with a few more Lewis structures on them and a little bit less explanation. See you on the next video.